Hello, my children. I am Professor Science Person, and today I have a very interesting lesson for you all as we delve into the complex nature of protein structure.
That sounds great.
Excellent. So let's return to the amino acid, the basic building block of proteins. Here it is, right here, with the N representing nitrogen atoms, the C representing carbon atoms, the H representing hydrogen atoms, and the O representing oxygen atoms. Now, the carbon here bonded to all these oxygens is known as the carboxylic acid group, and the N here bonded to these two hydrogens is known as the amino group. Hence, any chemical that contains both these two groups is known as an amino acid. The central carbon here is known as the alpha carbon, and the R here is the side chain we covered last time, referring to any chemical group bonded to the amino acid backbone that distinguishes the amino acids from each other, giving them different properties. Now, this is all good and true. However, it doesn't have much weight without the proper chemical background. So let's get into that.
The only chemistry I have is with my katana.
Ow. Wait, no, I'm not going to step on that now. So anyways, let's zoom into the forces that connect the different atoms in the amino acid. As we all know, atoms consist of negatively charged electrons orbiting a tiny positively charged core, known as a nucleus. Now, as these atoms bump into each other, it's possible for them to start sharing electrons, as shown here. However, these sharing of electrons, known as a covalent bond, are not very peaceful. You see, the nuclei of these two atoms are both trying to pull electrons over to their side. Now, the ability of these different atoms to pull electrons to their side is known as electronegativity. In other words, the strength of the two atoms in this tug of war is electronegativity.
Okay, but what happens when one of the atoms wins the tug of war?
Well, that's a hard question to answer, Caleb, because there's no quote-unquote winning. However, if an atom with a very high electronegativity is paired with one with a very low electronegativity, the electrons are almost completely pulled to one atom. This atom would then have more electrons, giving it a negative charge, whilst the other atom would have less electrons, giving it a positive charge. In this case, the electrons are pulled so strongly to one atom that practically there is no sharing of electrons. But due to their opposing attractions, like magnets with opposite poles, the atoms are still attracted to each other. This is known as an ionic bond and is very common in chemicals such as salts. However, in biological molecules, this exchange does not really occur barring a few given circumstances. But we do get situations where electrons tend to be more pulled towards one atom when compared to another, in what is known as a polar bond, with one atom being slightly negative and the other being slightly positive. Now, if we look at the atoms that make up amino acids, we see carbon, hydrogen, oxygen, and nitrogen. Carbon and hydrogen both have relatively low electronegativities of 2.55 and 2.2 respectively. These values are relatively similar, meaning there isn't any substantial charge in carbon-hydrogen bonds. Oxygen and nitrogen, on the other hand, have electronegativities of 3.05 and 3.44. Whilst these do not significantly differ from each other, though, they do significantly differ from carbon and hydrogen. Thus, when these atoms form bonds with carbon, and especially with hydrogen, partial charges tend to form, affecting their attraction to other molecules.
Well, as a proud gamer, I only find attraction as a distraction from my true calling of blasting noobs.
Okay, are you trying to ask about the relevance of these partial charges?
Sure, why not?
Evolution is concerning, but to be completely honest, this is a really interesting subject, so I'll just roll with it. So, these little attractions are not really important in small molecules like a single amino acid on its own. But when we add more and more amino acids to the molecule, we will see the molecule will tend to bend over backwards to help put these partial attractions next to each other to help create the weird and wonderful shapes that proteins like to form.
I see, but this fact alone does not quench my thirst for knowledge. Well, I don't know about that. This is quite interesting to me. Hush now, you arrogant beta. You know not of the mountains of wisdom that I seek. Oh, I'm really sorry. I didn't mean to be mean.
Caleb, it's okay to be interested. It's a good thing. However, in a weird way, Bartholomew is kind of right, at least about the partial charges. You see, we have been discussing these charges as if they are occurring in a vacuum, but we are studying living organisms, which are mostly made up of water. Water, as you know, consists of an oxygen atom bonded to two hydrogens, which, based on their respective electronegativities, is quite the polar bond. Additionally, hydrogen is the smallest atom, consisting of only one electron, which is being pulled towards the oxygen. Thus, the positive nucleus is pretty much exposed, making it very available for bonding to negatively charged molecules, like the oxygen atoms on other water molecules. These special interactions are known as hydrogen bonds and are one of the strongest interactions between molecules that is not an outright chemical bond.
Which means water can seal through the gates of Babylon to allow me to acquire the golden parallelogram.
Well, not exactly, but it does make water quite a hostile environment. You see, because you have so many water molecules forming strong hydrogen bonds to all these other water molecules, it's difficult for other chemicals to be able to wedge their way in. Because of this, other chemicals have to form bonds with water in order to be able to enter the water itself. Therefore, the ability to form these strong bonds with water is known as being hydrophilic, known as being attracted to water. The opposite means that you are repelled by water because you are unable to enter the water itself. Therefore, you are known as hydrophobic or repelled by water.
So carbon and hydrogen are only there to be repelled by water? That isn't very gamer.
No. Carbon can do a lot more than that. You see, carbon is the most important structural atom for life itself. It is able to form up to 4 different bonds with 4 different atoms and is able to form chains and rings on which other atoms can be added, providing God knows how many different combinations of molecules, all with different properties. Furthermore, carbon and hydrogen bonds are capable of doing a lot of things. Not only do they contribute to the water repulsion I mentioned a couple of seconds ago, but they also happen to provide a lot of energy that can be tapped into by us living organisms. For instance, a lot of the fuel we use in our cars and planes happen to consist of just carbon atoms arranged in lines with a maximum number of hydrogen atoms bonded to them. These are known as saturated hydrocarbons and are a very important fuel source in our industries.
So, Among Us?
Sorry, can you repeat that, please?
Oh, Group of Greats?
What? Okay. Excuse me. Who is speaking now?
Hey, come on, dude. We talked about this. League of Legends. It's League of Legends.
What's going on?
Well, first I am interested in this class. I never know when my associates in Roblox need assistance, so I hired an understudy so you would not be deprived of your favorite gamer. Didn't have time to interview him though, which is something I now regret. Hey guys, shut up, Gary.
Oh, okay. Everyone, please calm down. So, Gary, you're more than welcome to join us. The more the merrier, after all. And Death Reapers 666. I'm afraid I'm going to have to ask you to please attend and give this course more of a chance. I think it would be very interesting for you.
Very well. I am interested in learning about these chemical concepts and what exactly they have to do with amino acids and proteins.
Great point. So let's get into it. So for here, I'm going to show you some amino acids, and we can begin to see whether they are hydrophilic or hydrophobic. Now, small caveat, we can see that the backbone of the amino acids are always going to be hydrophilic because the backbones remain constant for every amino acid. And as you can see, it's clearly hydrophilic. But we're not talking about the backbone of the amino acid, but rather the specific unique side chain that defines what amino acid it is. These over here. The reason why this is important is because based on which amino acids are present on which protein will give it different properties, as we'll mention soon. Now, as you can see, leucine and phenylalanine specifically have side chains that are hydrophobic because they contain only carbon-hydrogen bonds. However, if we look at serine and asparagine, we can see that they are polar hydrophilic side chains because of the red bonds shown here. This allows them to interact with water using only their side chains, giving proteins different properties, which, as I mentioned, we'll discuss in a little bit. Now, whilst these hydrophobic properties are important, they aren't all the protein structure. In fact, there are some special amino acids with unique properties to give the proteins. Glycine over here, for instance, is the smallest amino acid. Because it's so small, it can essentially fit wherever, even in places that are filled and crowded with many atoms. This allows glycine to make the protein more flexible, allowing it to bend in conformations that other amino acids would find uncomfortable because there isn't any space. Thus, glycine is important to give some proteins wiggle room or form conformations or shapes that are quite unstable with any larger amino acid. Proline, however, is the opposite. As you can see, its side chain over here actually bends over backwards and interacts with the nitrogen of the amino acid backbone. This makes proline very rigid and thus not flexible. This is used in order to give proteins rigid forms so that it doesn't bend around too much. Also, it can be used to prevent proteins from forming certain structures in favor of other ones. Thus, proline is used to give proteins stability and decrease flexibility when it is needed. Cysteine, however, has another interesting property. As you can see here, it has a sulfur atom, which can actually form bonds to other cysteine atoms using only the side chain shown here. This is known as a disulfide bridge, and it allows cysteine atoms to bond to other cysteine molecules on other sides of the protein. This helps the protein fold on itself by these strong covalent bonds between the cysteine molecules.
Just surface level stuff. The knowledge that I require is that which defines reality itself.
Well, you're in luck, or at least I think you are. Anyways, we're going to discuss protein structure, specifically its various levels, starting with primary. Primary structure is essentially just the sequence of amino acids, one after the other. Amino acids, after all, need to bond to each other to form proteins, strong covalent bonds, known as peptide bonds, shown here. This is a peptide bond between two glycine atoms, and the peptide bond essentially repeats for all the amino acids. As you can see, the peptide bond is formed between the amino group of one amino acid backbone to the carboxylic group of the other. These amino acids are now technically known as residues because now they're no longer full amino acids, but rather bonded amino acids, now known as residues. So, this sequence of residues from beginning to end is the primary structure of the protein and determines the final shape of that protein.
More. I require more power.
Okay, fair enough. So let's go deeper to secondary structure. Secondary structure is essentially the shapes taken by amino acids due solely to the backbone of the residues. Let's take a look at an example. This over here, for instance, is a beta sheet, a typical example of secondary structure. As you can see, it is not formed by the R groups, which would be here, but rather solely by the backbone, the carboxylic and amino groups of the residue backbone. This is what allows secondary structure to form. Here we see an alpha helix, another typical example of secondary structure. Now, this is a bit more complicated. However, essentially, hydrogen bonding via the backbone of the amino acids is forming this helical shape. Now, there are more examples of different structures that can be formed solely due to the backbone of the amino acids, but these two are the most predominant secondary structures found in proteins. In fact, a lot of proteins contain these sheets or helices within their structure.
Where do those side chains come into play, more directly?
Harry, you didn't even make a witty Dark Souls reference. I gave you half a pizza for this. Come
Don't
on,
worry
man.
about him, Gary. You raise an excellent point. You see, side chains really come into play when we discuss tertiary structure, which refers to the bending and folding of many secondary structures due to side chain interactions. These can include, for instance, hydrogen bonds, like we mentioned before, between different side chains on amino acid residues in the protein, which will tend to distort the protein shape to favor the formation of these hydrogen bonds. But the tertiary structure can also include things like ionic interactions. What I mean by this is that certain side chains on amino acid residues can be positively or negatively charged, and the shape of the protein will distort in order for like charges to be away from each other since they repel each other, whereas opposite charges are closer to each other since they attract. And thus the protein shape will change accordingly. Side chains, as we mentioned before, can be hydrophobic and are thus repelled by water, and so tend to move to the core of the protein to be away from all those water molecules that repel them. This results in a core of hydrophobic side chains surrounded by hydrophilic amino acids, preventing contact between hydrophobic and hydrophilic molecules. These rules apply to a single string of amino acids, which so far I have been referring to as a protein. However, a lot of proteins used in our body are actually multiple polypeptides interacting with each other. Hemoglobin, for instance, contains 4 polypeptides, and the interactions between these different polypeptides make up the final protein structure. This is the final level of protein structure referred to as quaternary structure, which is the interactions between different polypeptides to form the larger protein.
And do all proteins have this quaternary structure?
Well, not all proteins are really made up of more than one polypeptide. Some proteins are made up of just one polypeptide and thus have no quaternary structure. Others still have no tertiary structure. This means that they're made up of regular repeating geometric units consisting of solely backbone interactions and thus have no side chain interactions distorting the molecule. An example of this would be collagen, shown here. Now, collagen is the protein found in your ligaments and cartilage and tendons, and it's important for giving them structure and support. It gives them strength. Now, collagen, as you can see here, is a fairly simple structure, a triple helical repeat that is maintained solely by the residue's backbones and their hydrogen bonding. Now, the reason why it's important for this structure to be so consistent is because it allows different collagen molecules to associate to each other to form bigger and thicker fibers. These are important for giving to collagen the structural stability needed in order for it to serve in your tendons and ligaments to make sure that they can support the strain placed on them. In fact, this is why a lot of proteins that do not contain tertiary structure are actually structural proteins, important for giving structural support, elasticity, or other mechanical properties to different tissues. Thus, these are fibrous proteins that are important for structural support. However, the proteins that do tend to fold on themselves in complex tertiary or even quaternary structures are known as globular proteins because they form such compact globules.
I don't know though. This all seems interesting, but how does this tie into protein functioning?
Yeah, I guess that's true. We still really have been just dancing around the issue of how proteins work within our cells. That being said, you now have the base information to really appreciate just how cool proteins are. So, with that, join me next time as we use various biological pathways to explore the true nature of protein functioning. Have a good day, guys. See you soon.